Okay, so let's figure out the pH at the equivalence point. We have sodium hydroxide and hydrofluoric acid. Sodium hydroxide is a strong base. Hydrofluoric acid is a weak acid. So we're going to get water like we always do, and we're going to get sodium fluoride. Now, the presence of the fluoride ion here, because remember this is aqueous, so again, what we really have here is F minus, and that F minus is the conjugate base of a weak acid. And it is important that you understand that this is a weak acid because that tells us that its conjugate would be a relatively strong base. So then that strong base is going to react with water as a kind of a secondary reaction. And that's what's going to cause our pH to go in the basic range at the equivalence point. So even though we've neutralized the sodium hydroxide with the hydrofluoric acid, we've produced a base. And that base will produce hydroxide. And so even though we use the term neutralized, we don't have a neutral pH. Okay? So the question is, what is going to be the concentration of that F minus so that we can kind of icebox it and figure out what the hydroxide concentration will be. So we want to know what is the molarity of F minus so that we can do the icebox and figure out the concentration of hydroxide, the POH, and the pH. So the thing we have to keep in mind is that the F minus was created by reacting the acid and the base together. And since we're at the equivalence point, that means that both the acid and the base are limiting. And I can use either one to figure out how many moles of fluoride I've made. Okay, so I'm just going to use my sodium hydroxide. So let's say I have my 25 milliliters, which is 0.025 liters of NaOH, and I want to know how many moles of F minus I have. Okay, so I can just do this using stoichiometry and using the molarity of the sodium hydroxide. So this sodium hydroxide is 0.12 molar, so that means 0.120 moles per liter. And then I can go straight from moles of sodium hydroxide to moles of fluoride, F minus. Because again, if I want to know the molarity of the F minus, I need to know the moles and the liters, all right? So basically this one is just going to be 0.025 times 0.12. Okay, so, oops. Let's see if I can bring that back. All right, there we go. So 0.025 liters times 0.12 moles per liter gives us 0.003 moles, right? So I have 0.003 moles of F minus. And then the next step is going to be to divide that by the volume of the F minus. Now keep in mind that these products, the volume of my products would be the sum of my two reactants because I'm putting together 25 milliliters of sodium hydroxide with 20 milliliters of hydrofluoric acid. So altogether, my total volume of my products, which include the F minus, would be 45 milliliters. And so down here on the bottom, I'm going to say, okay, so I have 0.025 liters of one reactant plus 0.020 liters of the other, which would be, of course, would be 45 milliliters or 0.045 liters. Okay, so my next step on the calculator is going to be to divide my moles by 0.045, which again would be the total volume for my fluoride. So 0.067, okay? So 0.067 molar fluoride. The whole reason that I did that calculation is because remember we said the fluoride being produced is what makes this pH not neutral. So now I have to do F minus, so this product right here, the sodium, this aqueous sodium fluoride, okay? Remember we said it's going to act as a base. Oops. It's going to react with water. Okay, and it is going to form hydroxide by taking the hydrogen from the water, and it's going to reform HF. Okay, and so I'm just going to icebox this thing, starting with the initial concentration of F minus that I just calculated. So 0.067, don't care about this. This is roughly 0, this is roughly 0. This guy is going down, these guys are going up by the same amount. And so, oops, there we go. So 0.067 minus x. Okay, so the last question, or the last tricky part of this, is that we don't know the Kb for F minus, okay? But the Kb for a conjugate base is equal to 10 to the negative 14 divided by, let's write this out, so Kb for F minus is equal to 10 to the negative 14 divided by the Ka of HF. So we always are able to figure out the Kb of a base if we know the Ka of its conjugate acid. And since F minus is not anywhere on our table, essentially it's like the stronger the acid is, the higher its Ka goes, the weaker its conjugate base is. So the lower its Kb will go. And so that's why this equation works the way it does. So I'm just going to simply find the Ka for hydrofluoric acid, which if I look on my table, hydrofluoric acid is right there, 6.8 times 10 to the negative 4. All right. So we're going to do 10 to the negative 14 over 6.8 times 10 to the negative 4. And that is going to give me the Kb for the fluoride, as a base. So even though I didn't have that on my table, by knowing the Ka of its conjugate, I can figure that out pretty easily. Okay, so let's go ahead and do that. All right, so let's go down here. So we're just going to do 10 raised to the negative 14. Oops, I did that the wrong way. Let me backtrack and do this as a fraction. 10, raised to the negative 14. And then on the bottom, I'm going to put my Ka of hydrofluoric acid. So 6.8 times 10 times 10 to the negative 4. All right, so I get about 1.5 times 10 to the negative 11 as my Kb for F minus. So 1.5 times 10 to the negative 11. And now I'm ready to find my hydroxide because hydroxide is X in this equation. So 1.5 times 10 to the negative 11 equals X squared over my initial concentration of fluoride, which is 0.067. And I don't have to subtract X here because X is going to be so small in this problem, it's not going to make any difference. Okay, so I should be able to just multiply both sides by 0.067. That takes care of that, and then take the square root. And so that gives me x equals, bring it back over here. So I'm going to go ahead and just to kind of keep my sig figs correct, I'm going to go ahead and go ahead and use my rounded KB value. So 1.5, square root of 1.5 times 10 to the negative 11. So times 10 to the negative 11. And then we are going to multiply that by 0.067. And that should give us our hydroxide. So 1.0 times 10 to the negative 6. Oh, this is going to be easy. All right, so x equals 1.0 times 10 to the negative 6 molar hydroxide. And so the negative log of that, so negative log base 10 of this number is just going to be 6, right? And remember, that's POH. So that means pH would be 14 minus 6, which equals 8. And I guess actually for sig figs, I should have, I think, 2, so 8.00. A lot of work, but the idea is when we have a weak base, or a weak acid, I'm sorry, we have its conjugate present in the product, and that conjugate needs to ionize with water to give us hydroxide, and that's why we don't have a neutral pH, even though we call it a neutralization reaction. Then the just exact opposite would happen if we had a weak base. We would end up creating the conjugate of that, which would be a relatively strong acid. All right, guys. So there you've seen an example, and let me know if you have any questions in class.